Welcome to the MOOC lecture series of the RIGHTWEIGHT project of the Interreg Northwest of Europe. Today I would like to discuss the subject of mass production using additive manufacturing and topology optimization. But first I would like to introduce myself. My name is Brat. I have a background in mechanical engineering and I'm a lecturer and researcher at Fontys University of Applied Science. My research focuses on large-scale 3D printing of composite materials, but I also have experience in 3D printing of metals. Our research focuses mostly on the kind of materials using in that processes, the design using process parameters, preparing the files for 3D printing, and finding very useful and interesting use cases for industry. But first our video. So in this video, you've seen multiple ways of additive manufacturing. But what is additive manufacturing? Additive manufacturing is making a product by adding layers of material on top of each other. So instead of paying for removing material, you're paying to add material. So working in a way to reduce the weight of your product is very interesting in the field of additive manufacturing. Because the more lightweight your product will be, the cheaper it will be in the end. When we have a look at 3D printing in comparison with conventional machining, you can see that the cost per item for conventional machining will increase if the product will be more complex. So more material needs to be removed. It results in a more higher in price product in the end. With additive manufacturing, the complexity is not necessarily a power that will drive the price of your product. So just by adding material, it doesn't matter if it's just a big field or it's only just a small part in that, it will result in the same price. Also looking at the batch size of those products, we can see that the price of a 3D printed product will be constant. When you compare it to conventional machining like milling or working on a lathe, you can see that most of the time the cost will reduce if your batch size will increase. For the 3D printing, which is only just the adding of material, the batch size will, the price of the batch size will be the same. This is a result of the printing time it will cost to produce a product in that. But why should we use additive manufacturing? And what kind of materials do we use for that? Here at Fontys University of Applied Science, we use multiple materials. First of all, we use the standard polymers like PLA, ABS, PET, PETG, polycarbonate, other materials. It's the standard FEM, fused deposit modeling materials. But we also work with composite materials. And the composites, because of the short fibers that we use in that, we are able to get higher strengths with less of a weight. The short fibers are embedded in a thermoplastic matrix, and this can consist of also the PET materials, PLA, polycarbonate, and some other very interesting polymers. We will also print into metal, and for that we use stainless steel of 316L. Our research focuses on three main 3D printing processes. So we have short fiber composite printing, which works with a very large extruder, very similar to injection molding, and you can see the multiple parts of that process. So we will start with some granulate we put into the hopper in stage 1. It will flow to my screw that's in a barrel with heater bands around it that can heat the material in there. It will bring it to a molten state, and with the screw the material will be printed out, pushed to the nozzle where it will be deposited onto a previously printed layer, and that will build up your product on your base plate. This is just a short fiber composite printing. So in my granulate is already the short fiber of maybe glass fiber, also carbon fiber. We also use basalt fiber, and we're currently looking into more sustainable products for that. So we can use quite a lot and quite a different amount of materials for that. Next to our short fiber printing, we can also do continuous fiber printing. And with continuous fiber printing, we can get even higher strength into specific orientations of our products. So we can influence with the direction of where my fibers are, the strength in certain directions of my product. For this process we use two nozzles, one for the fiber. This can be also glass fiber, carbon fiber, Kevlar, high temperature glass fibers in that. And we use a PA or nylon based matrix where they will be placed upon. The only problem that we have is that all those fibers are only in the XY plane of your product. So it will be built in the Z direction layer by layer, but my fibers can only be placed in the XY plane. And we have multiple ways of filling that same product. So what we can do, we can lay the fiber just around the contours of my product, also on the inner walls, only the outside, only maybe at the holes, or even isotropic in all of that layer that is newly deposited. So by making differentiations in where my continuous fiber will be placed, I can influence the strength of my product. What we need to do, normally you will design just a product. This will be the outside of your product, and that will be 3D printed. But with being able to place those continuous fibers, we have an extra dimension in producing and designing your product. So we do not need to produce the outside of your product. We also need to find out, well, should I reinforce my product? Then we can print it, and then it can be put in use. So those were just the composite printing techniques. I also can print in metals. For that I will use SLM. And it's a material printing process that uses a laser to melt metallurgical powder, in this case stainless steel, and it will build a product layer by layer. Over here my powder is stored, and with my recoder or roller I can push that material onto my build plate. A laser will scan the surface or the cross section of my product. It will lower itself a little bit. It will place a new layer of powder on top of that. It will scan it again. And so layer by layer, I can build up my material and my product out of this metal powder. Okay, so now we know which materials we can use. We know which processes can be used. But the main problem and main reason to use additive manufacturing is that it's able to make different products than just the conventional machining in that. So let's have a look at this first product that we can use as a case to study why we should use additive manufacturing. This is a piece that comes from the aviation or the aerospace industry, and is used for if I remember correctly, for a wing in an aircraft. This piece is just designed for CNC milling, and we want to reduce the weight of this part. And to do that, we need to first find out, okay, what's the main function of this product? And with the added benefit of additive manufacturing, and that mass production will result into saving money and also in use of this product, I think it's just a very good solution to find out if you're able to redesign this for additive manufacturing. Okay, so what would be the function of this product? In use, we would have different load cases. We have one load straight up in the vertical direction, a different load, a different force in the horizontal direction. We can also angle that force. So a lot of different forces act upon this piece. Also a torsional falls on there. And by defining all these different load cases, we're able to find out how my product should behave in the end. Also over here you can see I'm defining some interfaces, some faces of your product that will need to connect to other pieces of your full assembly. So you can see some holes where some nuts or bolts will be placed, and a connection piece that will undergo all these loads. Okay, so now we defined how my product should look like. And for finding a more lighter weight solution, we will be using topology optimization. What is topology optimization? It's the minimum mass. It's using a technique to get the minimum mass to fulfill all these load cases. So we get the lightest product that's still possible to support all these load cases out of it. And very important in that is there is no loss in strength. It is optimized for all the load cases that we have in that. So when we will be putting a different load on that, it isn't calculated for that, so it is more easily to bend. It has less strength in other load cases. But if you define your load cases correctly, this product is just as strong as a normally designed CNC piece. So the nice thing is with topology optimization, it will reduce the mass. This will reduce the printing time, also the material used in that, and this will result in a cheaper product. And also in use, let's say for example in a car, the weight will be lighter and it will also cost less when you are driving that car. But how does it work? Over here we have a starting position. I just have two holes and a piece of plate material. I will be defining my interfaces, and over there I determined I need a piece of material about 1 or 2 millimeters that is left behind to be sure there is a proper connection to my nuts and bolts. And then my software starts calculating. I also define a force in one of these holes, and with that it starts calculating what is the minimum material that I need to still withstand all those stresses that will be put into that material. So most of my material is only put under a tensile stress of that, and that will result in a much stronger connection. Most of the time, a product will fail under the forces of shear stress. So when my computer program has taken away a lot of material, I will have an end product for that. And that end product is much lighter. You can see a lot of materials removed when comparing it to the first product. So this will result in a much lighter product. This is the end in that, so we can use this product just for additive manufacturing, but you could also use this as an input for redesigning your parts for just CNC milling. So you can get a very good idea, okay, how can I use it to reduce the mass of my piece that I want to produce. In the left, we have that same starting position. So you can see those very light orange lines, and those were my design boundaries. So the product that I would like to get out of my topology optimization needs to fit in all those orange lines, so in the original volume of my product. And as you can see, the product that it came up with, it's quite a complex design. So it has a lot of organic shapes that are very hard to produce just with CNC milling. And when it's hard to produce with milling, a very good solution will be additive manufacturing in that. So when we compare these two products, the one 3D printed with a product just CNC milled, we can see there's a reduction of 75% in weight. It is quite an amount for only one piece in that. It is optimized for stiffness, so when I would be using this piece or the other one, the stiffness of these products will be the same. Other materials that are also possible to use in that is, for example, titanium. But topology optimization is not the only solution that we can use and that we can benefit from with additive manufacturing. We could also use lattice structures. And what are lattice structures? Those are very open or porous structures, mostly consisting of tiny rods and little connections between them to create an even lighter product out of it. So in this example, as you can see on the board, it's a combination between topology optimization and a lattice structure that forms that optimized design that we have seen already. But maybe we can use those lattice structures also for other things. So those structures are quite open and porous. And the benefit from that is when we want to make a connection with, let's say, for example, composite materials, that porous structure can be filled with, for example, a resin or maybe even some very short fibers consisting of glass fiber or carbon fiber. The nice thing is we can also influence that lattice structure. So this is just a static lattice structure. The design is all the same on this piece, but we can influence the porosity of that structure. And with that, we are able to reduce the peak stress at the connection between both parts. So we can make some very strong connections with inserts from titanium-made parts that are overmolded and connected to just a carbon fiber reinforced plate. So those are mostly only the mass productional aspects of additive manufacturing. But additive manufacturing has a lot more benefits than that. With additive manufacturing, we are also able to reduce the lead time of some products in that. So the result will be, normally, when you have a lead time of about 56 days, we can shorten that production time of a first try or a first prototype to maybe 10 days. And this is just from design to having a first prototype in your hands. So 3D printing can be a very good benefit in your overall designing process. It is also used to reduce cost. When I want, for example, want to use a mold, most of my molds cost about 40,000 to 60,000 euros. Lead time will normally be 6 to 8 weeks. But we tried already. We are able to 3D print a mold within 2 days for maybe half of the price. And as a result of that, we are much faster in production for testing new designs. The iterative design process will also be much easier to use in that. So normally when you want to have one mold, you pay that price, and then you find out you need to change something. It's a very costly and long process in that. And just by being able to shift this fast at a reduced cost, you can make much more and more iterative designs. There's also the benefit of mass customization. So what we can do, my process is not dependent anymore on some tooling. So I don't need a mold to produce certain parts in that. What I can do, I can just change my part, my design in that, and it will just be 3D printed, custom to the need of my customers. So what are some very interesting use cases next to all the things that we've already seen? So we can also print tooling and fixtures. You can print molds, you can print prototypes, you can print one-offs, custom things. So there are a lot of benefits in comparison to conventional machining. For example, last year I worked together with a student team of the TU Eindhoven, the TU Ecomotive. And for them, we 3D printed a dashboard for a car. So this dashboard is about 1.8 meters in length, and it's printed in about 7 hours in that. So it's pretty fast to get a first prototype just from a design of a CAD model as a first fully 3D printed part that you can try and test fit into a car. Not only this part was 3D printed, but as a result of all their efforts with all their partners in that, they were able to fully 3D print this car. Some other options that you can try to do is, for example, all these metal pieces. But this is also an example of topology optimization, where we've reduced a lot of the weight of the original design, and you can create quite some complex structures that are almost impossible to create with CNC milling. Some other benefits, let's say you have some spare parts that are not anymore produced, so you don't have any more of the molds for that. Maybe it will be sand casting molds or any of the original tooling needed for that. You can get a design or 3D scan an original part, and instead of making it the original way, we were able to produce the spare part just by 3D printing. So there are quite a lot of options that we can use and a lot of benefits with additive manufacturing, especially if you want to speed up the process of making new designs and also in reducing weight. But even some more interesting parts that we are currently researching and want to find out if it's possible, and we think it is that with the fiber placement we can steer it with the movement of a nozzle. So also comparing it to the with the continuous fiber materials in that, we will be able to influence the strength in certain directions. So we can make some more hinge-like structures in just the design of your part. So you can create flexures just in a single piece where you normally would use a hinge. So by using all these complex new structures and design strategies, by getting to know the process that we're using, we will be able to create some even more interesting and complex designs. So we can reduce the amount of parts needed to create a full assembly, So we can just, instead of using two parts that need to be connected with a hinge, I can just print it in one part instead. That will give the same results. So reducing assembly is also one of the benefits that can be used with additive manufacturing. I want to thank you for your time and have a very nice day. Thank you.